Good morning, everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. Let us continue our conversation on stability. Today, we will be talking about initially bent and eccentrically loaded columns. So far, we have discussed spring bar models, where the bars were perfectly straight, the member was considered as rigid, the solution was based on a set of algebraic equations. Following spring bar models, we talked about Euler columns. Here the columns are also perfectly straight and it obeys Hooke's law. The effective length factor K for different boundary conditions was established. The solutions was based on a set of differential equations. Following Euler columns, we also talked about columns with practical boundary conditions. Here also, we assume that the column is perfectly straight. The boundary conditions are idealized as linear and rotational spring stiffness, and the solution was based on matrix method. After that, we continued our conversation on column theories. The buckling of stocky and short columns are perfectly straight columns and must be determined by considering the inelastic behavior. Covered tangent modulus theory, double modulus theory, as well as Schoenle's theory. This again was considered as perfectly straight. But does this assumption hold good for practical columns? Right? So what are practical columns? Straight columns do not exist in actual engineering structures. Practical columns can be classified into two categories. One is minor out of straightness, another is minor eccentricities of loading. The minor out of straightness can also be called as initially bent column or crooked column. How do design codes take that into consideration? They take that into consideration in two categories. The first one is the initial bent or crooked columns is taken care by Perry's formula as well as in European steel design codes, as well as in IS 800-2007. The eccentrically loaded columns are covered by secant formula and American steel design codes take that into consideration. Now, let's talk on initially bent or crooked columns. The figure on the left hand side shows a column that is crooked, which is initially bent shape of the column. Y0 is the lateral displacement of the member. We assume the initial deformation of the member is given as Y0 equal to A sin pi x by L. So, when we take the equilibrium under a deformed configuration, we have the total deformation as Y0 plus Y, which is given by the blue color curve, which is the deformed shape of the column after the application of the load. Now, we take a deformation at a point x from the top. Since the bending stresses are caused by the change in curvature y double dash and not by total curvature y0 double dash plus y double dash, the internal moment is given as mi equal to minus ei into d square y by dx square, which is equal to minus ei into y double dash. It may be confusing to some audience why there is a minus sign here. The minus sign is determined based on the center of curvature of the column. Here the center of the curvature is to the left side of the column as indicated in the figure, which is opposite to the direction of the positive y direction that is given in the configuration. Therefore, it is given as minus, and the moment at the cut section is given as P into y0 plus y to take care of the equilibrium. Now, equating the above two equations, M external is equal to M internal, we have P into y0 plus y is equal to minus ei y double dash, which is again given as ei y double dash plus py is equal to minus pa into sin pi x by L. Here y0 is substituted as a sin pi x by L. We have ei y double dash plus p critical y is equal to minus p critical into a sin pi x by L. Now we divide the entire equation by ei, which gives you the value y double dash plus p critical y divided by ei equal to minus p critical by ei into a sin pi x by L. We substitute k square equal to p critical divided by ei. We further simplify this equation y double dash plus k square y equal to minus k square a sin pi x by L. Now we have the same equation repeated here for continuity. The general solution for this is y equal to complementary solution plus particular solution. The complementary solution is given in the left hand side. To solve this complementary equation, we take y double dash plus k square y is equal to 0. Substituting d square by dx square equal to capital D square, we have capital D square y plus k square y is equal to 0. So d square plus k square into y is equal to 0. D square plus k square is equal to 0 is a characteristic equation. The roots of it is given as d equal to plus or minus ki. Recall the roots of the form m plus or minus ni. The solution is e power mx into a sin nx plus b cos nx. In the above equation, m equal to 0, n equal to k. So, the solution y equal to e power 0x into a sin kx plus b cos kx, which again boils down to y equal to a sin kx plus b cos kx. Now, we take the right hand side to obtain the particular solution. Let c0 into sin pi x by L be the particular solution for the ODE. A transcendental function is chosen because the non-homogeneous part contains a trigonometric function, that is minus k square into a sin pi x by L. So, we have this equation d square y by dx square plus k square y equal to minus k square into a sin pi x by L. When we substitute the value c0 into sin pi x by L, we have d square by dx square into c0 into sin pi x by L plus k square into c0 sin pi x by L equal to minus k square a sin pi x by L. So, when we double differentiate that, we have minus c0 into pi by L the whole square into sin pi x by L plus k square into c0 into sin pi x by L is equal to minus k square a sin pi x by L. Now, we can replace the term pi by L the whole square and k square. We know that P critical equal to pi square EI by L square. So, pi square by L square becomes P critical by EI. We also know that k square equal to P by EI. So, when we substitute the above terms, we have C0 into minus PE by EI into sin pi x by L plus P by EI into C0 into sin pi x by L is equal to minus P by EI into A sin pi x by L. We can take the common terms, which is sin pi x by L and 1 by EI common, and we can remove that from the entire equation, which gives rise to the value C0 into minus P sub E plus P equal to minus PA. So, we have C0 equal to minus of PA by minus PE plus P. So, C0 equal to minus of A divided by minus P sub E by P plus P by P. Substituting alpha equal to P by PE, which is the ratio of the applied load to the Euler load, we have the equation C0 equal to minus of A by minus 1 by alpha plus 1, which again can be simplified as C0 equal to minus alpha A divided by minus 1 plus alpha, which is A alpha divided by 1 minus alpha. So, the particular solution is C0 sin pi x by L equal to A alpha divided by 1 minus alpha into sin pi x by L. So, the total equation is y equal to A sin kx plus b cos kx plus alpha by 1 minus alpha into A sin pi x by L, where alpha equal to P by PE, where P is the Euler load, which is equal to pi square EI by L square. The boundary conditions are y equal to 0 at x equal to 0, y equal to 0 at x equal to L. So, when we substitute y equal to 0 at x equal to 0, we have 0 equal to A sin k0 plus b cos k0 plus alpha divided by 1 minus alpha into A sin pi of 0 by L. So, which indicates that 0 equal to 0 plus b plus 0. The reason is that sin of 0 is 0, cos of 0 equal to 1, and this third term alpha by 1 minus alpha also contains the sin term, which is 0. So, we have 0 equal to 0 plus b plus 0, which indicates that b equal to 0. Now, substituting b equal to 0 in the general equation gives rise to the equation y equal to A sin kx plus alpha by 1 minus alpha into A sin pi x by L. Now, we can again substitute the equation further, which is boundary condition 2, y equal to 0 at x equal to L. We have 0 equal to A sin kl plus alpha by 1 minus alpha into A sin pi L by L. So, this becomes 0 equal to A sin kl plus alpha by 1 minus alpha into A sin pi. In this equation, sin pi is equal to 0. So, when we substitute this, we have this following equation 0 equal to A sin kl. If sin kl equal to 0, then P equal to PE, and this is not the case to be investigated. Therefore, A should be equal to 0. So, which gives rise to the equation y equal to alpha by 1 minus alpha into A sin pi x by L. So, y naught equal to A sin pi x by L, which is the assumed initial deformation of the member, y equal to alpha by 1 minus alpha into A sin pi x by L. But we need to know the total displacement. The total displacement is y sub t equal to y naught plus y. When we substitute that, we have A sin pi x by L plus alpha by 1 minus alpha into A sin pi x by L. which indicates that when we take a sine pi x by L common, we have 1 plus alpha by 1 minus alpha. This gives rise to the equation y total equal to a by 1 minus alpha into sine pi x by L. So the total deflection at midspan is y sub t equal to delta at x equal to L by 2. So when we substitute at x equal to L by 2, the total displacement is delta. So delta equal to a by 1 minus alpha into sine pi L by 2 by L, which gives rise to the value delta equal to a by 1 minus alpha, because sine pi by 2 becomes 1. Now delta equal to a by 1 minus p by pe, because alpha is the ratio of the applied load to the Euler load. So delta equal to a by 1 minus p by p Euler. So when we plot the graph between alpha, which is the ratio between the applied load and the Euler load in the y-axis, and mid-height deflection delta in the x-axis, we get the following curve. A equal to 0.1 indicates lower imperfection and a equal to 0.3 indicates higher imperfections. The observations are, unlike perfect columns, initially deformed member begins to bend as soon as the load is applied. Deflection increases slowly at first and more rapidly as p by p sub e increases. Larger initial deformation, which is A, indicates larger total deflection at any load, but as applied load reaches Euler load, deflection increases without bound regardless of initial deformation. Point number 4, the carrying capacity of an imperfect column is always smaller than the Euler load regardless of how small the initial deformations are. Members with large initial deformations results in large deflections, which produce inelastic strains and can be expected to fail considerably below the Euler load. Now, having completed crooked columns, let's look at eccentrically loaded columns. You can see on the left hand side, we have an eccentrically loaded column with an eccentricity E. If you take the cut section at a distance x from the top, we have the internal moment mi equal to minus ei d square y by dx square is equal to minus ei into y double dash. The moment at the cut is m sub e equal to p into e plus y. Equating the above equations, we have m sub e equal to m sub I, which indicates p into e plus y is equal to minus ei y double dash. So ei y double dash plus py equal to minus pe. We divide the entire equation by ei. We have y double dash plus py by ei equal to minus pe by ei. Substituting k square equal to pi, we have y double dash plus k square y equal to minus k square e. The solution is y equal to a sin kx plus b cos kx minus e. Now, the first two terms a sin kx plus b cos kx is complementary. The term e is particular. How did we get that? Let a constant c be the particular solution for the ordinary differential equation. A constant is chosen because the non-homogeneous part here is a constant, that is e. We have d square y by dx square plus k square y equal to minus k square e. So when we substituted y equal to c, we have d square into c divided by dx square plus k square into c equal to minus k square e. Differentiating a constant once or twice leads to the same value, which is 0. And then this k square can be eradicated. Now we have c equal to minus e. Now let us find the values of constants a and b in the general solutions for y. We have the boundary conditions are at 1, y equal to 0 at x equal to 0. The second boundary condition, y equal to 0 at x equal to L. Substituting boundary condition 1, we have y equal to 0 at x equal to 0. We have 0 equal to a sin 0 plus b cos 0 minus e gives rise to the value b equal to e. Now y equal to a sin kx plus e cos kx minus e. Boundary condition 2, y equal to 0 at x equal to L. So 0 equal to a sin kl plus b cos kl minus e. Substituting b equal to e, we have 0 equal to a sin kl plus e cos kl minus e. We have 0 equal to a sin kl plus e into cos kl minus 1. So this gives rise to the value a equal to e into 1 minus cos kl by sin kl. Substituting b equal to e and a equal to e into 1 minus cos kl by sin kl, we had the general solution y equal to e into 1 minus cos kl divided by sin kl into sin kx plus e cos kx minus e. This can be further simplified by taking e outside. We have 1 minus cos kl by sin kl into sin kx plus cos kx minus 1. The total deflection at mid-span is equal to y equal to delta at x equal to L by 2. We have delta equal to E into 1 minus cos KL by sin KL into sin KL by 2 plus cos KL by 2 minus 1. Here we are simply substituting instead of x, we substitute L by 2. We also know the trigonometric equations that sin KL equal to 2 sin KL by 2 into cos KL by 2 and cos KL equal to 1 minus 2 sin square KL by 2. So, using these trigonometric identities, we can further simplify the equation delta equal to E into 1 minus 1 plus 2 sin square KL by 2 divided by 2 sin KL by 2 cos KL by 2 into sin KL by 2 plus cos KL by 2 minus 1, which again simplifies to minus 1 and plus 1 gets simplified out, and then 2 gets cancelled, and then we have that sign on the top and the sign on the denominator gets cancelled. We have delta equal to E into sin square KL by 2 divided by cos KL by 2 plus cos KL by 2 minus 1. We take LCM, we have delta equal to sin square KL by 2 plus cos square KL by 2 by cos KL by 2 minus 1. We also know the identity sin square theta plus cos square theta is equal to 1. So, we substituted 1 here. So, delta equal to E into 1 by cos KL by 2 minus 1. 1 by cos is secant. So, we have delta equal to E into secant KL by 2 minus 1. We also know that K equal to root of P by EI. So, when we substitute that, we have delta equal to E into secant root of P by EI into L by 2 minus 1. We know that the Euler load P Euler is equal to pi square EI by L square. So, the EI can be written as PE into L square by pi square. So, when we substitute the value of E equal to PE into L square by pi square, we have delta equal to E into secant of root of P divided by PE into L square by pi square into L by 2 minus 1. We can further simplify and get the equation delta equal to E into secant pi by 2 into root of P by P Euler minus 1. Now, when we plot that with respect to mid-height deflection, we have delta, which is the mid-height deflection at the x-axis, and alpha, which is the ratio of applied load divided by the Euler load. We have the following graph on the left-hand side. The E equal to 0.1 represents lower eccentricity and E equal to 0.3 represents higher eccentricity. Okay, look at the origin. The origin is at the same place where the curve starts. Unlike we have a Perry's formula where there is a small deviation. The small deviation is because in a crooked column, the values actually do not start exactly at 0. They start at little away from the axis, which is based on the amount of imperfection that is present in the column or the amount of crookedness that is present in the column. So, let's look at it. The observations for the eccentrically loaded column. Comparison of these curves with those of the initially curved columns indicates that the behavior of an eccentrically loaded column is essentially the same as that of an initially bent column. In both cases, bending begins as soon as the load P is applied. The deflection increases slowly at first and then increases rapidly as P approaches Euler load P sub E. At P equal to P sub E, the deflection delta increases without bound. Columns with large eccentricities E deflect considerably at loads well below the Euler load, whereas columns with very small eccentricities of loading do not bend appreciably until the load is fairly close to the Euler load P sub E. A column with relatively small eccentricity of loading can therefore be expected to support loads only slightly less than the Euler load. On the other hand, a member with large eccentricities will collapse at loads considerably below P sub E. Thank you everyone. We will continue our conversations on buckling in the next class. Thank you.